Hello everyone, welcome to the Chemistry channel. So today we're going to be starting our second lecture on atomic structure, and we are going to be mainly focusing on the concept of the quantization of energy. Now in the last video we talked a lot about the wave theory of light. However, this time we're going to be talking about certain concepts in which the wave theory of light does not describe. So with that, let's begin. So in the previous lecture, we talked a lot about the wave theory of light. However, the wave theory of light is not perfect. It does not describe some important observations that we see in day-to-day life. So the first thing that the wave theory of light does not describe is something called black body radiation. The second thing that it doesn't describe is the photoelectric effect. And the third thing that it does not describe is emission spectra. So in this video, we are only going to be talking about these two things. So we're only going to be talking about black body radiation and the photoelectric effect. We're not going to focus on emission spectra until the next video. So with that, let's talk about these first two things by first describing black body radiation. So what is black body radiation? So in order to describe black body radiation, I have here a little figure that I drew. So I don't know if you've ever done this, but if you've ever done this, imagine taking a steel or iron rod and imagine taking that steel or iron rod and putting it over a fire for a great deal of time. So what do you think is going to happen to that steel rod? So after putting that steel rod over the fire, of course the steel rod is going to heat up. And after a certain amount of time, and when the steel rod heats up to a certain temperature, you'll see the steel rod glow red, as we see here. And this glowing red is actually called black body radiation. So black body radiation is defined as the emission of light from a heated object. So black body radiation is the emission of light from a heated object. So whenever you take a fire poker or a steel rod, stick it in fire, and then it glows red after some time, that is black body radiation. So why would black body radiation not be described by the wave theory of light? Well, it's because when physicists looked into black body radiation, they noticed that lights of different colors actually emitted different temperatures. So they actually emitted different heats with different temperatures. So for example, a red light may be cooler than a white light, or a certain type of light may be hotter than another type of light. So basically, the physicists noticed that different types of light emit different temperatures. So some wavelengths of light are different temperatures from other wavelengths from light. So physicists noticed that the wavelength of radiation determined its temperature. However, they did not know how wavelength determined temperature. And the wave theory of light says nothing of this. So basically, physicists noticed that different wavelengths produce different temperatures. And the wave theory of light says nothing about this. So this perplexed physicists for a long, long time. And they did not figure it out until a man named Max Planck came around. So Max Planck in around 1900 proposed that energy is emitted and absorbed in packets. So you may have heard of this before. And he called these packets of energy quanta. So quanta are the smallest amounts of energy that can be emitted or absorbed. So quanta are the smallest amounts of energy that can be emitted or absorbed. So he basically proposed that energy is absorbed and emitted in these packets of energy, in these discrete packets of energy. And he found that the energy of light is directly proportional to its frequency. So this means frequency. So he found that the energy of light is directly proportional to its frequency. So after a lot of derivations, he came up with this equation, that E is equal to H times F. So H is actually called Planck's constant. So Planck's constant is approximately equal to around 6.626 times 10 to the negative 34th joules times seconds. And F is, of course, equal to the frequency. Okay? So, what does this E represent? Well, this E represents a quantum of energy. So this E represents a quantum of energy, a packet of energy. So a packet of energy is equal to Planck's constant times the frequency of the light. So what does this equation tell us? Well, it tells us two things. So the first thing that it tells us is that as the frequency of the light increases, the energy increases as well. And as the frequency of the light decreases, the energy decreases. So basically what he's saying is that energy is directly proportional to the frequency of the light wave. Planck, though, also said that energy is emitted and absorbed in only whole number, so this means number, multiples of quanta. So in other words, energy is only absorbed in whole number multiples of quanta. Therefore, you can only absorb energy in this type of form. So dot, dot, dot. So for example, if you absorb only one quanta of energy, you say H mu. So note that this mu is also another symbol for frequency. So frequency often in textbooks is given either as mu or F. So these, note that mu and F mean the same thing. So basically what he's saying is that energy can only be emitted or absorbed in specific quanta. So in whole number quanta. So in other words, if you absorb energy, you can only absorb it in one quanta of energy, two quantas of energy, or three quantas of energy. So energy can only be emitted or absorbed in whole number multiples. So I know this probably doesn't make too much sense. So I came up with an example, and this is a very famous example that a lot of textbooks use. So imagine that you are walking up the steps, right? So you walk up the steps. So each step is around 100 centimeters high. So imagine that each one is around 100. Actually, that's pretty big. So let's decrease that a bit. So imagine that each step is maybe 30 centimeters high. And in order to go from one step to the next, you have to climb up 30 centimeters. So this step is 30 centimeters, this step is 30 centimeters, and the next step, so forth. So in order to climb up each step, you have to go up 30 centimeters. Now this means that you have to increase your potential energy on each step. So what does that mean? So potential energy, if you're in physics you may already know this, is potential energy is equal to the mass of something times the gravity constant times the height. So mgh. So that is the potential energy. So as you go up each step, your potential energy increases. So the potential energy associated with each step, so the difference in potential energy associated with each step is correlated to the change in height. So therefore, in order to go from one step to the next, you have to increase your potential energy by 30 centimeters each time. So in other words, in order to climb from the floor to step 1, you have to go up 30 centimeters. That correlates to a potential energy value. So let's just say going from, let's erase this. So let's erase this. I think this will be a good way to visualize this. So imagine going from the floor to step number 1, right? So the height difference between the floor and step 1 is 30 centimeters. So therefore, your potential energy, the potential energy would increase from 0, so this is your potential energy, to m times g times 0.3 meters. So your potential energy would increase from 0 to mg times 0.3 meters from the floor to step 1. However, the same thing is required from step 1 to step 2. So in step 1, your potential energy is mg times 0.3 meters, and in step 2, your potential energy is So you go from step 1, where your potential energy is mg times 0.3 meters, to step 2, where your potential energy is mg times 0.6 meters, and so forth. So what is this saying? So what if I want to go from the floor to step 2? How would I get there? Well, the energy difference between each step is, so the energy difference, so we'll symbolize this as the change in P per step is equal to m times g times 0.3 centimeters, because each step is times 0.3 meters, not centimeters. So because each step is 30 centimeters. So in order to go from the floor to step 2, the energy difference would be equal to 2 times this amount, because you're going up 2 steps. So it would be 2 mg times 0.3 meters. So what is this analogy trying to tell you? This analogy is trying to tell you that in order to go from one step to the next, you have to go in whole number multiples of this potential energy. So in order to go from step 1 from the floor to step 1, you'd have to increase your potential energy by this factor. If you want to go from step 1 to step 2, you'd have to increase the energy by the same amount. However, if you want to go from the floor to step 2, you would have to double the amount of potential energy to go from the floor to step 2. So this is basically saying that in order to go from one step to the next, or to go up from 2 steps above, etc., you need to increase your energy by whole number multiples. And the same can be said for energy absorbed or emitted in the quantum world. Energy can only be absorbed in whole number multiples. So if you want to go from one energy level to the next, and let's say they're just separated by h mu, you have to increase your energy by h mu. So in order to jump from this level to the next. However, if you want to go from this level to a level that's separated by 2 h mu, you have to increase your energy by 2 h mu. So you can only increase your energy by whole number multiples. I hope this makes sense. Okay. So we can actually use this equation, E equals hf, to come up with a very important equation. So let's give you a different color here. So the equation that I'm about to derive is actually very important for general chemistry. So we start off with E equals hf. However, we know from our last video that c, which is the speed of light, is equal to lambda, which is the wavelength, times the frequency. So we can solve for the frequency by using this equation, where c over lambda is equal to f. Therefore, we can substitute this equation into our main equation. And this will give us E is equal to h times c over lambda. And then we can rewrite this as E is equal to hc over lambda. So this right here is a very important equation in general chemistry. And this is because this equation is super important because it relates wavelength to the energy of something. So therefore, we can say that as frequency increases and wavelength decreases, the energy must increase, right? So why does this make sense? Well, recall that F, frequency, is equal to c over lambda. As wavelength, and remember this from the last video, as wavelength increases, frequency decreases. And as wavelength decreases, frequency increases. Therefore, the same should be said for energy. Since energy is directly proportional to the frequency, as frequency increases, the energy increases. And since frequency is inversely related to lambda, as lambda decreases, frequency must increase, and therefore energy must increase. And the opposite is true as well. As frequency decreases and lambda increases, energy must decrease as well. So this is very important. This equation is very important for predicting the energies associated with different wavelengths of light. So now let's actually talk about what this equation is saying. So it's important to note that this equation is only talking about a single photon. So let's write that here. So the E equals HF, which equals HC over lambda, is only talking about the energy associated with one, let's change, I misspelled with, so let's get rid of that. Cut here. With one photon. So what is a photon? A photon is actually a particle of light. So the equation above that Planck derived is only talking about the energy associated with one photon of a particular wavelength of light. So remember that there's many different wavelengths of light, and here I have 3 different wavelengths of light, and each of these wavelengths is characterized by a photon of a different type of light. So here we have a photon associated with red light, here we have a photon associated with green light, and here we have a photon associated with purple light. So let's compare the wavelengths of each of these types of light. So let's look at the red light first. So the red light has this long of a wavelength. Now these are not to scale. Green light has this long of a wavelength, because remember, wavelength goes from either peak to peak or trough to trough. And then violet has the smallest wavelength. So based upon the relationship above, which type of light do you think has the highest energy? Hopefully you said violet has the highest energy, and that's because violet has the lowest wavelength. And this lower wavelength allows violet to have a higher frequency. As we can see here, there's many more wavelengths for the violet light than there is for the green light or the red light. Therefore, violet has the highest energy, green has the medium energy in this case, and red has the lowest amounts of energy. So therefore, Planck's equation describes the energy of a single photon at a particular wavelength. So always remember, it's very important to remember that this equation only describes the energy associated with a single photon at a particular wavelength. It does not describe multiple photons. It only describes the energy associated with a single photon at a particular wavelength. So it's also important to know how to find the energy of 1 mole of photons. So this should be photons, not protons. Sorry about that. So photons. To find the energy of 1 mole of photons. So let's find a way to calculate this. So we know that the energy of 1 photon is equal to hc over lambda. And it's really easy to find the energy associated with 1 mole of photons. And all you have to do is multiply this value by Avogadro's number. So this means Avogadro's number times hc over lambda. And this will give you the energy, so let's label this energy associated with 1 mole of photons. And remember that Avogadro's number is equal to 6.02 times 10 to the 23rd atoms, or anything. So remember, Avogadro's number is just an amount. But in this case, we're talking about atoms or photons, electrons, etc. So it can be anything. And whenever you have 6.02 times 10 to the 23rd of anything, you have a mole of something. So this allows you to find the energy associated with 1 mole of photons being with a particular wavelength. Okay, so now that we have an understanding of how energy is quantized and how to solve for the energy associated with a particular photon, we can now apply these ideas to the photoelectric effect. So let's describe what the photoelectric effect is. So here we have a beam of light hitting a solid metal cube. And when the beam of light hits the solid metal cube, what happens is, if the beam of light has enough energy, it can cause an electron to escape from the metal atoms within the cube, and this electron, this escaped electron, can actually be put into a wire, and this wire can deliver a current into a light bulb or something, and the light bulb can light up, or you can power something else. So the photoelectric effect basically describes how light energy can energize an electron enough that it has enough energy to escape from the atom and go into the space around it. So this idea, in 1905, Einstein applied Planck's theories to the photoelectric effect. However, Einstein stated that in order for electrons to escape from the atom, it must be supplied with enough energy from the incoming light, to escape the atom. So in order for the electron to escape, it must be hit with enough energy in order to overcome the attractive forces of the atom. And he called this minimum amount of energy the work function. So the work function is defined as the minimum amount of energy required for an electron to escape the atom. So the work function describes the minimum amount of energy required for an electron to escape the metal. So how is this work function calculated? Well, it's actually the exact same equation that we talked about earlier. So the work function is equal to Planck's constant times the required frequency of light needed to allow an electron to escape. So Fr is equal to the required frequency of light needed for an electron to escape. So this frequency here is the frequency of light needed for an electron to escape. So in order for an electron to escape, it must absorb at least the same amount of energy equal to this work function. So in order for the electron to escape, it must absorb the same amount or greater energy than the work function. So Einstein related the work function to kinetic energy of the electron escaping. And from high school, you may remember that the kinetic energy of something is the energy associated with the movement of something. And it's given by the equation 1/2 m of the object times the velocity of the object squared. So 1/2 mv squared. And Einstein stated that if the incoming light has an energy, so this means energy greater than the work function, the excess energy is converted to kinetic energy. So therefore, he came up with this equation where E is equal to the kinetic energy of the electron. So this means electron, where E is equal to h f of the incoming light, so this means f of the incoming light, minus the work function. Therefore, we can come up with a couple of conditions. If the energy supplied by the light is less than the work function, the electron is not able to escape the atom. However, if the energy supplied by the light is equal to the work function, then the electron is able to escape the atom. And if the energy supplied is greater than the work function, then the electron has kinetic energy and it escapes the atom. So those different conditions are very important to know for general chemistry. However, if you understand where this equation comes from and the concepts associated with it, you should not have to memorize any of this. So the last topic I want to talk about is the brightness of light. So what about brightness? Does brightness affect the energy of an electron? So let's show a little diagram here. So here I have two lights. This bigger red light is associated with a brighter light, and this little one is not as bright. And here we have two metal blocks. So let's say brightness can be defined as the amount of photons hitting a certain area over a certain time. So therefore, this brighter light won't have as much photons. So actually, let's use red, because we have some red light here. So let's get rid of this. So some red light. So this less bright light, so this is less bright, is emitting less photons per unit time. So let's illustrate it as like this. However, this really bright light is emitting a ton of photons per unit time, and therefore it can cover a greater surface area of the metal. However, is there any difference between the energy of the electrons leaving this metal and the electrons of the energy of this leaving this metal? What do you think? Are emitting red photons, right? And these red photons their energy is only correlated to their frequency and wavelength. Since these two lights are the same wavelength, they are emitting the same energy. And the same energy is causing the electrons to come off of the metal with the same amount of energy as well. So the brightness plays no role in the energy of the electron leaving the metal. All it does is increase the amount of photons hitting the metal. All it does is increase the amount of photons hitting the metal per unit time. That's all brightness does. Therefore, brightness does not affect the overall energy of the electron. It only affects the amount of photons hitting the object per unit time. So brightness is only defined as the amount of photons hitting an object per unit time. So since E is equal to HF, which is equal to HC over lambda, brightness plays no role in the energy of an electron. It only affects brightness only affects the number of photons hitting something. So so it can increase the number of electrons leaving the metal at a certain amount of time, but it can't affect the energy of a electron leaving. It can only affect the amount of photons hitting an object and the amount of electrons leaving the object at the per unit time. So that is all the concepts for today. And to end off this video, I have 3 practice questions for you. They're actually relatively easy. It sort of covers the concepts from both the last video and concepts from this video. So what I want you to do is I want to encourage you to pause the video and try these questions for yourself. And I'm going to go over these now. So, if a photon has a wavelength of 500 nanometers in a vacuum, what is its frequency? So remember that all light in a vacuum travels at the same speed, and this speed is at the speed of light. And here I said c is equal to 3.0 times 10 to the 8th meters per second. So let's solve for frequency. So we know, so let's actually get rid of this circle. I'm sorry about that. So we know that mu, which is equal to the propagation speed in this sense, is equal to the frequency of some of the light times the wavelength. However, since we are in a vacuum, the speed of light is constant, and it's equal to c, which is equal to f times lambda. Now we just solve for f. C over lambda is equal to f. So when we set this equation up, so f is equal to 3.0 times 10 to the 8th meters per second over the wavelength. Now this is where the tricky part comes in. Since the velocity is in meters per second, you need to convert this value, the 500 nanometers, to meters. So here we're going to put 5.00 times 10 to the negative 7th meters. And this is the same value with the same number of significant figures as the value on top. Instead, we're in meters. This allows us to cancel the units out. So when you plug this in your calculator, the meters cancels out. And when you plug this in your calculator, you should get something around f is equal to 6.0 times 10 to the negative 14th. So, I'm sorry, to the positive 14th, not the negative 14th. So let's get rid of this. Times 10 to the 14th inverse seconds. So that is your frequency. And note that this has the correct number of sig figs because we have 2 here and 3 here. And therefore our final measurement should have 2. So in the next question, a photon has a wavelength of 749 nanometers. What is its energy? So since we're only talking about a single photon, we can use E equals hc over lambda. So then we can just do a plug and chug. So H is equal to 6. I said this early in the video, so 6.626 times 10 to the negative 34th joules seconds times 3.0 times 10 to the 8th meters per second over, now remember we have to put this in meters, so 7.49 times 10 to the negative 7th meters. So let's cancel out units. So meters cancels out because this is in the denominator and this is in the numerator. Seconds cancels out because this is in the numerator and this is in the denominator, and we're left with joules, the unit of energy. So when you plug this in your calculator and conserving the amount of sig figs, because here we have 4, here we have 2, and here we have 3. After putting this in your calculator, you should get a value of around 2.7 times 10 to the negative 19th joules. So that is your energy. Okay, so the last one is the hardest out of the three. And here I am asking you to derive an equation relating the velocity of an electron leaving a piece of metal to the frequency of incoming light. So here it requires a knowledge of the photoelectric effect. So remember that the kinetic energy is equal to H, or the Planck constant, times the frequency of the incoming light minus the work function. So we know that this E is equal to the kinetic energy. So we can set this equal to HFI minus W. And we know that the kinetic energy is equal to 1/2 mass of the electron times the velocity of the electron squared, equal to HFI minus W. However, we know that we can rewrite this as Hc over lambda, because Fi is equal to C over lambda I. So 1/2 MEVE squared is equal to Hc lambda I minus W. So now all we got to do is solve for V. So what you do is you do some algebra. So MEVE squared is equal to 2 times the whole thing, so Hc over lambda minus W. And then you divide by Me on both sides, the mass of the electron. So VE squared is equal to 2 over Hc lambda minus W divided by the mass of the electron. And then you take the square of both sides, giving you V is equal to the square root of 2 times Hc over lambda minus W divided by the mass of an electron. And this will give you the velocity of your electron leaving the metal block. So guys, that is it for today. Thank you for watching this video. Next time we're going to be getting into emission spectra, and then after that we're going to be starting to get into atomic structure. So we're getting closer and closer to understanding atomic structure. So please be patient. This is all very important in order to understand atomic structure. I thank you for watching, and I hope this helped you. Please post any questions in the comment section that you have. Thank you for watching.